we are assuming that the parameter to be estimated is random and is characterized by an a priori probability density function. So, we have a parameter, it's different from the maximum likelihood. Essentially, when we have a maximum likelihood, we don't know what is a parameter, and so, whatever comes out for us is the right estimate. That's for the maximum likelihood. So what we do, we write the likelihood function, we optimize the likelihood function, and if by making the likelihood function, it comes out a parameter value that, is somewhat meaningless, we don't do anything. Okay? We can make a post-processing, like take it out or similar, but that post-processing implies that you are using some a priori information. So before starting again, if you remember when we discussed about the frequency estimation, during the frequency estimation we said the frequency in a sample signal is limited between minus pi and pi. And so since the frequency is limited between minus pi and pi, we are looking for the frequency being between minus pi and pi. Okay? So we were searching in that interval. Now, implicitly doing that, we were using an a priori information, which is saying that, I'm searching for the estimate bounded between two values. So when we're doing something similar, we are using some a priori information. In that case, we are using the a priori information that the estimate of the frequency is limited because of the way that I sample the signal, because of the way that I define the normalized frequency and so on. Okay? Now, another example, assuming that I'm estimating the direction of arrival of the signal, okay, and assume that I have a set of sensors, okay, for those that yesterday were at the Huawei meeting. So I have a set of antennas, okay, and so for the reason related to where the users are, where the transmitters are, like the Wii, the play Wii, what is that, the game, okay? So the Wii expects that you are in front of the Wii. Now in that case, the system that estimates your position and then from your position estimates the parameter necessary for the Wii to play with is based on the fact that there are some a priori information which is related to where the user is supposed to be. Now, so this has all to do with a Bayesian estimation method. Now, in formula, it's trivial, so it's very stupid, But my goal is not to show you how is the formula because you can read yourself, but to let you enter into the concept. Now, let me make another example about the jargon. Okay? I don't know if I made this example, a few weeks ago when we introduced the estimation theory, but it's worthwhile to stress the concept. So now the algorithms that estimate the position of the target, like the position of a mobile phone, let me switch off. The position of the mobile phone, okay, so are based on the fact that every time this guy is transmitting, okay, there are a set of receivers that are receiving. So all the receivers around are estimating, or might estimate, the time of delay that takes the signal to go from here to there. Okay? So, this time of delay is estimating, the locus, which is related to all the points that have the same time of delay. So that means that, this cashier, that means that if I have a transmitter here, transmitter can be a person shouting, can be like when there are a thunderstorm. I don't know if you compute on the thunderstorm, the distance from the lighting, from the position of the lighting with respect to yourself. in order to understand if the thunderstorm is approaching to you, okay? If you have a house and you need to care about the house, so perhaps it's something that you look at, because I mean, if the thunderstorm is really on the top of you, and if the lighting comes to your house, it's not a safe situation to stay close to the TV, or perhaps you unplug the TV and you make some of the triggers, stupid procedure that everybody does. So if if you see the thunderstorm approaching, you see the lighting, and then you compute the time, so it takes 1 millisecond takes to go from the lighting up to you. Okay? Now, so that means that if I am recording that signal, now it takes some time, which is the time of delay, to go from here to there. So the time of delay, let me say tau I, okay, here this is the I to the receiver. So tau I can be correlated, which is very, very trivial, with respect to the distance, di. So di is the distance between from here to there. Now, of course, you don't know tau, so you estimate tau. You don't know the distance, then estimate the distance, okay? Now, when this guy here estimates the distance, it doesn't know where this guy is. So, it's all around a locus, which is, it's all everywhere within the radius of the distance di. So if I take if I have another receiver, J, and if this receiver J is measuring the delay, from the delay I estimate the corresponding distance, then I don't know where it is. Once again, the distance is all the radius with a radius of dj, and it's everywhere, because my signal has no direction. Now, making this way, when I compound everything, so I have another receiver here, which is the OM, and then I compute the distance, then from the distance I have the locus, then all this is making an estimate of the position. Good. Now, what I'm doing is a maximum mapping, because I'm not putting any a priori information where this target might be. Okay? Because imagine that the goal is to estimate my position, of my phone. Okay? Actually, I made the wrong mistake. I made the wrong example. So my phone, when I keep in my pocket. Okay? Now, if you need to estimate where is my phone when I keep in my pocket, and you assume as an a priori that because of the time, because of blah blah blah, so I need to stay in this room. So there is an a priori knowledge about where I am. There is an a priori knowledge about where is my position now. And so because of that, you can establish this a priori information, which in principle can define where is my position regardless of any measurement. So you can make the estimate of my position regardless of making no measurement, without making any measurement. So if you want to establish what is my position without making any measurement, that means that you know something about it. Now, this is something can be that the room is D22, okay? So establishing, the probability, then you can say that the professor is in D22. Good. But now, we know that the room is, is arranged with the table this way. And then what I can expect? I can expect that, professor this time of the day should be around this position, okay? So the probability that I am in this position is higher than the position being there. Is even much more high than the position being there on that that terrace or whatever. Okay, so what I'm describing a priori information. So I can say that I can locate my position using this method, but I can say, wait a minute, if all that is measuring my position, since this one is representing this room, now this is the room, this is the wall of this room, this is the table of this table here, and this is the input there. Okay. Oh, that's the aperture. Okay. Then I mean, they're all tables there. Fine. So without any a priori, it says that I'm there. But it's unlucky. So if I use my a priori information says that I mean the professor should be most likely around this area during the lecturing time. So what I can do, I can use this information as a priori information constraining, which means this estimate should be moved there in some way, in such a way that I combine the measurement with the a priori so that I get the information, which is an estimate, after making a measurement by, let's say, a set of a receiver around. Now this one is after making the measurement by whatever is the device, is called a posteriori. So a posteriori information is when I combine the a priori information, which is the probability area where I'm staying, with the measurement that are carried out by whatever, set of a receiver around. So now how to combine that. So it's a kind of intuitive that I can combine a priori with the measurement. But how do I make it mathematically? Now, before making this combination, which is, there is a way to make it, but I don't know how right now. So before making that one, since this is this room, this is the table, this is all the area where I'm moving, okay? So if I don't make any measurement, and I'm asking you, where is the professor now? Assume that you are outside. And you want to do the position, you want to do the measurement, where is the professor? But before making the measurement, you want to guess where I am. And so what you are going to do, you say that, it's very likely that, the professor is going to be in this part of the room. But now you say, no, professor is using the slide. And he has a table and there is a cable. So since there is a cable, everything I'm saying happens before opening the door, before making any measurement, before positioning, locating my mobile phone, which is in the pocket. Okay? So before that, you say, there is a cable here. Now, the blackboard is halfway on the right or the left. There's a chair. Usually, this chair is here. You see, usually means a priori. So when I say there is usually a chair here, since there is a chair here, the professor doesn't jump onto the chair, and it doesn't move the chair much. Okay. So if I need to describe the distribution of the professor, I might say that the professor is mostly likely there. Okay, if standing. If sitting, then there is another, blob as a maximum of the probability, which means a sitting. And with the lower probability, the professor is going on the other side of the board in case he needs more room. Okay? So what I'm describing here is the probability where I am a priori. Okay? A priori means, without any other information about the data. So cutting. Imagine that I cut it. Okay, the probability is going to be something like a small probability, then a peak, and then a large one. Okay, probably this is higher. Okay. Yeah. So this is the distribution. By the way, this distribution of probability is not Gaussian. First of all, it's not Gaussian. Okay? So, up to now, we have been talking about Gaussians. We introduced the Laplacian. We started to say, if it is Laplacian, then, my metric, my optimization function has to do with the L1 norm, which is the absolute value. but since the absolute value is complicated to manipulate, so I try to use the quadratic optimization, which means I try to use the Gaussian assumption as much as possible, and then in the worst case I use a robust estimation. Now, what I'm saying is that the a priori might not be Gaussian, and so we need to know how to handle that. Now, it's out of any question that Gaussian is much more simple, is popular, is useful, and we will start with that. But we need to face the case that the a priori is not Gaussian. Perhaps the information about after measurement might be Gaussian, but we will see. So so now this distribution is before any measurement. Okay, that's the probability. So if the parameter is theta, this probability before any measurement is called p theta, and theta, in this case is, let me call theta y and theta x. Okay, so theta is a set of parameters, theta x and theta y. Okay. So I have two parameters here, and that defines my position, so the position where I am. So this probability is the probability density function of the position in x and y, so theta x and theta y, before making any measurement. Now this one is called a priori. Okay, a priori means before. Okay. So now we are making measurement. Oh, so when we make a measurement, okay, we are getting a new set of values. So when we measure something, which is this one, okay, then we get x. X are the measurement. I get some data. Now when I have the data, that's my goal. My goal is to establish the probability density function of theta, which is my parameter. But now is after measuring the data, after measuring something. Now when I say after measuring, so these are the data, and this is after measuring x. So I measure x, which means, I establish the triangularization of the position where I am. I try to make some sensor that is measuring where the professor is. I do some measurement, okay? Now, so this probability density function is the probability density function of my position after measuring. Now, when I say after measuring, that measurement is taking this probability, which is p theta. This probability is the probability a priori, which means, the distribution of where I am, where professor is, okay, a priori. Okay, a priori means, I don't do any measurement. I know the time of the day, so I say this is the distribution. Now I can get a new probability, which is the probability of theta after making the measurement. Now this probability of theta after making the measurement can get, a distribution that might be something like this. Now, so what is this probability density function? Now this probability density function is, since I make a measurement, and making a measurement is an operation that I do explicitly, this is called a posteriori. A posteriori means after making measurement. After collecting data, after getting something, okay? Now, So assume that I look at this, I look at that. So this is the professor, position of professor in the room before making any measurement. You are sitting at home, you are not making any measurement, you, for some reason, you are sick, you stay in bed, and you say, oh, where is it going to be now? I mean, you draw something similar in your mind. You don't write in a paper, you know, you make it's mental. Now, assume that you make a measurement. Now, this measurement can be, for instance, a WeChat or a web, WhatsApp. So, you know, you get a WhatsApp, okay, and someone says, he's sitting, okay, or I don't know, he's on the other side of the board. Now, since you get this information, you say, okay, then you know it should be this side. So combining this WhatsApp or WeChat information with your a priori means that I'm not there, I am this side. Okay? Now, since this X now becomes a message from WhatsApp or WeChat. So, what is the probability density function of the position of the professor after the WeChat or WhatsApp message? Okay? Now, of course, you know, I'm making a set of a heuristic. I will be rigorous like later. Okay? So now, you know, imagine that you sketch a behavior like this. So, after having this behavior, you can establish a metric which says, now I need to say where is the professor. Okay? So, because this one is the distribution, the position of the professor after the WhatsApp or WeChat message. Okay? Now, but where is the professor? Now, it's up to you. You need to decide a metric. So the metric can be, so I choose as the position of professor the maximum of this a posteriori probability. Now, the maximum of this a posteriori probability sets the value of the position, this one is position, such that the corresponding probability is maximized. So that one is the maximum of what? Of this probability. Since this probability is called a posteriori probability, so that one is the maximum a posteriori. And so this one is theta at maximum a posteriori. This is called MAP. Okay? So, you know, then if you say, what is the position, where is the position of professor? Now, according to the MAP criteria, which means according to the maximum posteriori probability criteria, the position is there. I don't know, here. Okay. Now, why is here? Because, you know, I keep moving there, then, you know, my corresponding probability is growing, and then it gets bigger. Now, you know, I might define a new metric, and this new metric says, well, this distribution is this way, but you know, I mean, there are some tail here, and the tail are kind of long. So let's do this way. Let's compute the mean for that. Now, if I compute the mean means that the area here is the same as there. Now, I exaggerate, okay? But you know, the area here is the same as there. That's the mean. The concept of the mean value is that, you know, is computing the value such that it's barycentral with respect to the right and the left. Okay? Now, if I calculate this mean, then, you know, I establish a new position. Now, this new position is the mean, so which means it's half a way of the importance of different tails like there, with respect to the tail on the right. So the tail on the right and the tail on the left. Now this mean, the mean of P theta given X, which is the mean of a posteriori probability, which is the mean of the probability of data after, the probability of a position after the data, after the WhatsApp. after the reach up, after opening the door, after measuring with the multilateralization method, which means, you know, looking many sensors, after whatever. Now, this means that the experiment goes here. So X is not collecting just the data, but is collecting the experiment. This is where goes the experiment. Okay? Now, when I get this one, I calculate the mean. But the mean, you know, says that if the professor is here, this one is an error. If the professor is there, this is an error. So since I am half away, this estimate, which is the mean of that, we will prove in in half an hour that this estimate is also the minimum mean square error estimate. So the barycentral position is the minimum mean square error estimate, which is called minimum mean square error estimate. So once I give you the a posteriori probability, you can define either the estimate of the parameter according to the maximum posteriori criteria, okay, which is the maximum, or the barycentral criteria, which is the minimum mean square error. What you need is the a posteriori. Now let's see how this is carried out. Now, informally it's kind of straightforward, but let me help you to read. So the a posteriori PDF, okay, is the probability density function after the observation, after the experiment, okay? The observation now, is the experimental data. And I say observation means, I'm collecting some experiments on it. And so this experimental data reflects the physics, okay, reflects the specific setup that I'm using. So, this is the behavior. So the a posteriori probability, which is now described more formally, the a posteriori probability is the probability of the set of parameters data after, I read it this way, after making a measurement, when a measurement is equal to xk. So that means that I'm making one measurement, and then I can get an estimate. Now, this can be written according to the bias formula. So it can be written as the probability of the measurement given the set of parameters, so parametric with respect to the parameter, multiplied by the a priori probability, which is p theta, which means the probability, which I establish before making any other assumption. Okay? So according to the bias formula, it's divided by the probability of x equal xk. Now, I prefer to revisit, and it's very common to revisit, this a posteriori. So I have p theta given x equal xk is equal to a scaling factor gamma. This scaling factor, which is 1 over px, okay? This scaling factor gamma ensures that everything multiplied has a meaning in terms of probability. So which means that the area should be 1. To make it simple, okay? So now so now we have this part, because we know this is p theta, so this p theta is a priori PDF. And so this is px given theta. Now what is this px given theta? Now this one is a conditional PDF. But this conditional PDF, which is highlighted there, it resembles to me something. That one resembles to me the Laclede function. So when I use the Laclede function, I parameterize the probability density function of the observation with respect to the set of parameters that were theta here. And then what I did, I plugged the specific observation into X, and I solved to maximize with respect to theta. And that was the maximum likelihood method. So this conditional PDF resembles the likelihood function. Okay, that one resembles the likelihood function. Now, putting together one on the top of the other, okay, which is what I sketched. So, assume that my a priori is behaving in this way, which is of course not Gaussian. And assuming that my px given theta, so my conditional PDF is shaped, is behaving this way. Now, if you don't look at the bottom, so if my conditional PDF is behaving this way, and if I want to estimate the maximum likelihood, then I take this conditional PDF and I find the maximum for that. That is the maximum likelihood. The maximum likelihood is the maximum of Px equal xk, so one measurement, parameterized with respect to theta, and finding the maximum for that. So it's the maximum of that with respect to theta. Okay, this is exactly what I sketched there. So if my conditional PDF has this behavior, this is the maximum likelihood. Okay, so look at here. The maximum likelihood does not include any information about the a priori. So how I use the a priori? Now it's simply taking this and multiply by that. So take the conditional PDF and multiply by the a priori information. Now when I multiply the two, in this complicated plot, okay, so I tell you what is the meaning of the complicated plot. So all the dashed line in this complicated plot is representing the probability density function of the a priori, in this one, and the conditional there. So when I combine, means I multiply one by one, okay? So which means here is 0, and then it comes out to 0 as well. Here is the maximum, okay? So if the maximum is multiplied by something, perhaps it is a maximum, but it's not at the top of the maximum anymore. Okay, so it's not the largest one. So when I multiply, it comes out something in this shaded area here. Okay, so what I computed here is the a posteriori, where a posteriori means after collecting data, is the a posteriori probability density function. Now my goal is to calculate my position. My goal is to estimate the parameter. So how do I estimate the parameter? Now to estimate the parameter, I can calculate the position of the maximum. And the position of the maximum, is the maximum of the a posteriori, and the position, which is the coordinate here, is the maximum a posteriori estimate. So we say that this is the theta map. Theta map is the maximum posteriori estimate of the parameter theta. Now in formula means that theta map is the argmax with respect to theta of the posteriori probability. So I search for the maximum, the position of the maximum with respect to theta of the posteriori probability. The position of the maximum gives me the theta map. Now, the other way, I can look at and search for the barycentral position. Barycentral means this area should be equal to the other one. Okay? So all this area here should be approximately, at least in the plot, should be equal to the other. Now, so the value that is making the two areas the same is the mean. And so theta NMSE is the mean of P theta given x, okay? Which we usually write expectation of theta given x equal sk. Now you know we will drop x equal sk in the next, and then we simply write expectation of theta given x. Okay, that's it. That's the mean. The mean of px p theta given x. We will write simply as expectation of theta given x. Okay, which is is the mean. So now the MMSE. Okay. So in formula, the MMSE is this expectation, okay, or by simply computing the mean is the integral of theta on p theta given x, which is the posteriori theta in theta. Now, so that's we understood, at least now we understood how to include the a priori. So the new part is how to insert the a priori into px given theta, which is something that we know. Into px given theta is the essence of maximum likelihood estimate. Okay, so we knew how to make the maximum likelihood. Now we include now the a priori information. Now let's.
Professor, sorry.
Tell me.
What was the line that divided into?
It is the line that I used to divide here or there.
But to have equal areas?
Oh, it's the mean.
Okay.
Yeah, the mean is simply the value which is splitting the two parts. Okay, that's a mean. Two area. And the two areas are the area of the probability. Now let's make an example. Okay, so let's start with an example. Simple example. It's clear? Okay. Let's make it with a simple example. Let's make this simple but very useful model. Okay. This model is so simple, it is so stupid, that is covering much of the important aspect and is covering some of the misunderstanding. Now, assume that I have one sample. So my model is x, which means theta plus w. Now theta is Gaussian, w is Gaussian. Okay? Now theta is my parameter, w is the noise. So I know a priori that theta is Gaussian. So this means that, I know a priori that theta is normal with a certain mean and a certain dispersion, certain variance. So now, if I ask you, what is the value of theta without making any measurement? What you're going to say is, I know nothing about this. So, the best estimate of theta is theta mean. This first moment, okay? So if I make no experiment to say this is the best estimate of theta, that's before making any measurement. So I'm manipulating I'm simply using the a priori information. Now, so let's see the experiment. So assume that I make one experiment, okay? And so, if I consider one experiment, and now consider that this x is equal to one value. Now, what is the maximum likelihood? If I make the maximum likelihood estimate, you can write the likelihood estimate, you can maximize the likelihood estimate with one value, and you say that the maximum likelihood estimate of theta is the value itself. What is the variance of that estimate? The variance of that estimate is the spread of the noise, which is sigma squared of the noise. No. Okay, fine. This is, let me say, the non-Bayesian estimate. which means not using p theta, so the a priori. Okay? I'm not using that. But now the a priori says, wait a minute, you know, theta is distributed as normal with a certain mean and a certain variance. So what we do, we put together. So we put together, you know, the conditional PDF with the a priori information. And we divide about the probability of x. So that one, you know, is, I mean, theta is Gaussian. We can write the joint probability. Now, this is a Gaussian one, this probability. This conditional PDF is what we use for a Laplace function. Okay, that is Gaussian as well, because this one depends on the noise, if you remember. Okay, so this one was the probability of the noise shifted to theta. Okay, so recall that. Now, when I put together, okay, and I simplify, which is, if you go to the book, you can see the passage. If I simplify, what I get is here. What I get is, you know, I mean, the product of two terms. Okay, so that is the probability of the noise shifted by theta, x minus theta, yes, here. And the other is the a priori. Okay. Now you know, this division by the probability density function of x goes into the scaling factor. So I have d, which is part of the scaling factor. Okay. And here I have the conditional PDF, and here I have the a priori. I multiply. So I start multiplying and collecting, grouping the terms. So when I group the terms, it comes out. Oh, I skipped the passage. So when I group the term, it comes out that this one is a Gaussian that depends on x with the first moment and the second moment. This comes because I compound the term. Nice, so you know, this is what I write here. So the a posteriori is Gaussian. Now, this Gaussian depends on a function gx and on sigma 0. Now, let's look at that. Gx is equal to a function that depends on theta naught and x. You know, rewriting is equal to theta naught plus a scaling factor multiplied by x minus theta naught. And sigma 0 is equal to, you know, a set of combination, but this one is the variance of theta given x, which is the variance of the a posteriori probability. Now, so this variance of the a posteriori probability comes from a combination of the variance of sigma w and the variance of sigma theta. Sigma theta is the priori, sigma w is the noise. Now, looking at this one, you know, this a posteriori